Hello students. Today we are going to see about a design of one-way slab. Okay. So before entering the problem, so you have to know what is one-way slab, what is two-way slab, uh, the load distribution in one-way slab, and the arrangements of reinforcement arrangements of one-way slab, the design steps, all those things you have to know while designing a one-way slab. Okay, so I will play a video for it. Okay, so please watch very carefully. After that, we can go for design problem. Okay. So this is the load distribution of one-way slab. So for one-way slab, while acting uh, or it is subjected to a uniformly distributed load, it will bend like this. Okay, the load distribution along one direction, that is shorter direction. Okay, therefore we can provide a main reinforcement along shorter direction only. Okay. Okay. Uh, that reinforcement is called as main reinforcement. Okay. So the structure, the bending structure, is noted. So the center of the slab uh, will be bent due to positive bending moment, and the edge of the slab will be hogged due to negative bending moment. Okay, therefore the main reinforcement should not be provided as plain bar. Okay, so it will uh, bend 45-degree at a particular span. Okay, that is also called as crank. Okay, the main reinforcement only will be cranked. Okay, the transverse direction, that is the perpendicular direction of main reinforcement, is called as distributor, which is why the distributor is provided in slab is to reduce the stringage of the slab. Okay, that reinforcement is called as distributed. I will show you. So please watch very carefully the reinforcement. This is the main reinforcement. The bent portion is called as crank. Okay, which is uh, uh, bent in one end only. Okay, it will bend alternatively. So alternative reinforcement will be cranked likewise, which is provided in bottom. Okay, so the this is the shorter reinforcement. So the shorter reinforcement will be provided in bottom. Okay, the transverse reinforcement, that is distributed over, provided over it. Okay, this is a this is a distributor which is plain reinforcement. Okay, you will not you need not bend uh, like main reinforcement in distributor. Okay, this is the cross section of a piece. Note this. This is the cross section of a slab reinforcement. The uh, actually the crank will be provided at one end for one reinforcement. Okay, in cross sectional view, it will be it will be shown like this. Okay, uh, the white reinforcement is called as main reinforcement. The dot, that is a distributor, is provided over the main reinforcement. Okay, please note this cross section of slab reinforcement. I play again. The load is distributed in only one direction, that is along shorter direction. That's why we put main reinforcement along the shorter direction only. Okay, therefore uh, crank the reinforcement will be cranked in main reinforcement alone. Okay, uh, you will not be cranked in distributor. Okay, here distributor act as just to reduce the shrinkage. Okay, this is most important. uh, you should be provided a gap between main reinforcement and outer edge of the slab, because if it is not provided the gap in slab, the reinforcement will expose to environment, so it may be corroded due to uh, air or moisture, anything else. Okay, so that's why we put a gap between reinforcement and outer edge of the slab, that is called cover. Okay, so you may have seen cover block in site also. Okay, now we can go for design. So Uh, so what are all the design steps are available for designing a one-way slab? So all those things you have to know. So first thing is slenderness ratio. So slenderness ratio, this is used for defining a slab, whether it is a one-way slab or two-way slab. Okay, then permissible stress. So unit first is fully based on working stress method. So it is fully based on stress. Okay, stress only considered, material stress only considered, so not strain considered. Okay, So you have to know about permissible stresses of materials. Okay, so that is second step. Then depth of slab. Okay, so normally practically 5 inches to 6 inches of thickness will be provided for a slab. Okay, so uh, this is third step, depth of the slab. So which is arrived from deflection formula. And fourth step is effective span. Effective span means shorter span. Okay, shorter span. Then fifth step is load calculation. Then sixth step is bending moment and shear force calculation. Then check for effective depth. Then main AST calculation. Then distributed reinforcement calculation. Then check for deflection. The last one is detailing. So this is the design procedure for one-way slab. Okay, so so let's see one by one. So first step is slenderness ratio, which is denoted as lambda. So this is a ratio between longer span to the shorter span, Ly by Lx. Here the problem is given, so read very carefully. The room dimension is 3 by 7 meter. 3 meter is shorter span, that is Lx. 7 meter is longer span, that is Ly. And also the slab is supported by 230 wall thickness, and live load is given 1.5 kilonewton per meter square. Normally we can use 1.5 to 3 kilonewton per meter square for residential building. Then materials graded are given, M20 grade of concrete and Fe415 HYSD bar. HYSD bar means high yield strength deformed bar. Okay, so first step is slenderness ratio Ly by Lx, longer span to the shorter span 7 by 3, 2.33, which is greater than 2. So please keep it in mind. So uh, if slenderness ratio greater than 2, then you will go for one-way slab. That slab will be designed as one-way slab. If slenderness ratio less than or equal to 2, then you can go for two-way slab. That is, that slab should be designed as two-way slab. Okay, here the slenderness ratio is 2.33. Therefore you have to design a slab as one-way slab. Okay, the second step is permissible stresses. So for permissible stresses, so uh, so the permissible stresses concept, we have already uh, uh, seen in previous videos. uh, Permissible stresses for concrete and permissible stresses for steel. So both the values should be known while designing a slab. Okay, so please keep in mind, this is the permissible stresses of concrete. Here two terms are used. One is sigma CBC, another one is sigma CC. Sigma CBC means permissible compressive stresses of concrete due to bending. Okay, then permissible stresses of uh, compressive stress of concrete in direct, that is sigma CC. Okay, uh, uh, while calculating sigma CBC, we use factor of safety as 3. Similarly, while calculating sigma CC, we use a factor of safety as 4. Okay, so how to obtain it? For example, M20 grade of concrete, the sigma CBC value is 20. 20 means characteristic compressive strength of M20 grade of concrete. 20 divided by corresponding factor of safety, that is 3, which is equal to 6.66, that is a round up value 7. Similarly, sigma CC equal to 20 divided by 4. The factor of safety value will be vary for sigma CBCC and sigma CC. Okay. Similarly, sigma ST means permissible stresses for steel. Okay, for FE 250 and FE 415. So both grade of concrete we have to arrive it. Up to 20 mm dia, we use factor of safety as 1.8. That is sigma st equal to 250 by 1.8, 140 newton per mm square. 250 means fe 250 yield strength. Here fe 415, therefore sigma st equal to 415 divided by 1.8, that is 230 newton per mm square. If it is if diameter is greater than 20 mm dia, the sigma st value will be varied, that is 130 for fe 250 and 230 for fe 415. Okay, this is the formula for finding the design constant, which is used for designing a slab, that is q j k, then small m and capital ast. Okay, small m means modular ratio, the most important this formula which uh, which will help you for attending various uh, examination, various examination. Okay, that is 280 divided by 3 sigma cbc. Okay, then bending moment equal to mqbd square. This is the table, those values, that is sigma cbc, m, k, j, q, those values are arrived from this formula. Okay, so we can go for problem directly. So second step is permissible stresses for M20 sigma CBC, which we have already seen in above the table. Sigma CBC equal to 7 Newton per mm square. Sigma ST for FE 415 equal to 230 Newton per mm square. Then J equal to zero point 0.9, Q equal to 0.91 for combination of M20 and FE 415 steel. Okay. Then third step, depth of the slab. So which is initially we uh, assumed for one way slab, we don't know what is the area of reinforcement, so we initially assume pt value, that is percentage of reinforcement, as zero point 0.4. Okay, as per is 456 2000, the minimum reinforcement, sorry, minimum percentage of reinforcement is 0.12 percentage. Okay, uh, but here we assumed that pt equal to 0.4 percentage, the corresponding kt equal to 1.25. Okay, the kt means modification factor for tensile reinforcement, which is arrived from the graph uh, shown in is 456. This is page number 38, figure 4. Okay, this figure consists of 5 curves. One is fs 122, 145, 190, 240, 290. Okay, fs means design stress. So the formula for finding fs is given below, 0.58 fi AST required by AST provided. Okay, but here we don't know the AST required and AST provided. Okay, so how to fix fx value? So for fe 415, the uh, what is that, sigma st value, what is that, sigma st for uh, fe 415 230 newton per mm square, so it is nearer to 240, therefore we fix fs as 240 newton per mm square, and also we assumed PT value, percentage of reinforcement, that is x-axis value 0.4 percentage. So that vertical lines touching Fs equal to 240 curve, then corresponding y value modification factor, that is KT value, will be read out. Okay, so this is 1.25. This is 1.25. Okay, and the depth of the slab, will be arrived from deflection formula. The deflection formula as per IS for codal provision, page number 37, L by D max equal to L by D basic into KT into KC into KF. Okay, KT equal to modification factor for tensile reinforcement, KC equal to modification factor for compression reinforcement, KF equal to modification factor for flanged beam. Okay, for simply supported beam, according to IS 456 page number 37, LBT basic value for simply supported beam is nothing but 20. Page number 37. Please read out. Yeah, this is given. Basic values for L by D value for cantilever 7, simply supported 20, continuous 26. So here the slab condition is simply supported. That's why we take L by D basic value as 20. Okay. So therefore L by D equal to 25. So from it we can find small d, which is nothing but 0.12 meter, that is 120 mm. Okay. Uh, then we find overall depth, capital D value. So capital D value, how to find it? So capital D, which is nothing but small d plus uh, main reinforcement, half of the main reinforcement dia plus clear cover. Please see this image. Please this see this image. This is the cross section of the slab. Capital D is denoted as overall depth, and small d is denoted as the effective depth. Okay. The this is the bottom reinforcement is main reinforcement. The rounded bar is distributed, which is over the main reinforcement. Okay, the effective depth means the distance between top of the slab to the center of the main reinforcement diameter. Okay, okay. Therefore, capital D, how to find it? So, which is nothing but add small d and half of the diameter of main reinforcement plus clear cover. Normally 15 mm will be provided for slab. Okay, therefore overall depth equal to small d plus half of the diameter. So practically in slab, main reinforcement diameter uh, will be provided as 10 mm, and distributed diameter will be provided as 8 mm diameter. Okay, please keep it in mind. Okay, so therefore overall d equal to 140 mm. Then effective span. Effective span means, as per codal provision, least of clear span plus effective depth and center to center distance of support. Clear span given, shorter span 3 meter, and effective depth we have already found, that is 0.12 meter. That's therefore 3.12 meter. Then center to center of distance 3.23 meter. And that means the center to center, the support thickness 230 mm, here 230 mm, left hand side 230 mm, right hand side 230 mm. So center to center means 230 by 2 plus 3 plus 230 by 2. So overall center to center equal to 3.23 meter. So among these value 3.12 meter is the least value. Therefore effective span, take effective span is 3.12 meter. Okay, the next step is load calculation. So please keep it in mind. So load calculation should be calculated in terms of kilonewton per meter. Okay, so what are the loads to be acted on a slab? That things should be known to you. So first one is self height of slab. So how will we find the self height of slab? Okay, so slab thickness, we know the slab thickness. Okay, so that is overall depth 0.14 meter. Here mentioned as zero point 0.4. This is not correct. Actually this is 0.14. Okay, the overall depth 0.14. And also you have to mm, know about the load, that is the slab design should be in 1 meter width. Okay, so 1 meter width, therefore 0.14 into 1 into unit weight of RCC, that is 25 kilonewton per meter cube. The unit weight of RCC equal to 25 kilonewton per meter cube. So we will get 3.5 kilonewton per meter. Okay, then live load value is given in your problem, that is 1.5 kilonewton per meter square, which will be converted into kilonewton per meter, that is multiplied by 1 meter width. And uh, floor finish normally we take the ranges between 0.75 to 1 kilonewton per meter square. Here we take 0.75 kilonewton per meter square. Similarly we have to convert into kilonewton per meter, uh, that is multiplied by 1 meter width, which is then we will get 0.75 kilonewton per meter. Then add these three values, therefore total load equal to which is denoted as W, 5.95 kilonewton per meter. Okay, the next step is bending moment and shear force calculation. Bending moment, which is denoted as a capital M. This slab is simply supported, therefore the formula is WL squared by 8. W is total load, L is effective span, which is already arrived, that is 3.12 meter. So final value is 6.99 kilonewton meter. Then V, shear force, which is denoted as V, the formula is WL by 2. Okay, so the value of shear force is 8.97 kilonewton. Then check for effective depth. This is most important because we assumed the percentage of reinforcement. Okay, so the depth of the slab, whether we check whether the depth of the slab is correct or not. Okay, so we check from the formula like M equal to Q BD square. Okay, the required D equal to root of M by QB. Q is a design constant, which is already seen in earlier. Okay, and therefore root of 6.99 into 10 power 6. So kilonewton meter, which is converted into Newton mm, therefore multiplied by 10 power 6 divided by Q value 0.91 for combination of M20 and Fe415, B equal to 1 meter width, therefore 84.64 mm required depth, required effective depth, but we provided 120 mm. Okay, so we know that uh, we should provided the
the provided D should be greater than the required D. Please keep it in mind. The provided depth, whenever provide the dimension, it should be greater than the required value. Okay, so here required value is 84.64 mm. Okay, therefore uh, but our we provided D equal to 120 mm, which is greater than 84.64 mm. Therefore our dimension is okay. Okay, the next step is calculating main AST reinforcement. So the formula is to find the AST equal to M divided by sigma ST JD. M is nothing but bending moment. Sigma ST is nothing but yield strength of steel for Fe415. J design constant for combination of Fe415 and M20. D equal to effective depth. So apply those values and get required AST value, which is nothing but 281.4 mm square. Okay, so we provide the detailing of main reinforcement from IS 456 1978, that is SP16. So please read very carefully. So here the required AST equal to 281.4 mm square. Okay, okay. So SP16 page number 230. Please take page number 230. So the left one value is spacing in terms of centimeter. The top row is bar diameter. Okay, 6 mm, 8 mm, 10 mm, 12 mm, and all the values are in terms of centimeter square, that is area of reinforcement. Okay, but uh, we need in terms of mm square. Okay, so all those values will be converted into mm square. Okay, so our record value is 284. So concept is the provided AST should be greater than should be little bit greater than the required AST. Okay, so this is main AST. So I said earlier the main reinforcement diameter as 10 mm 10 mm dia. Practically we use main AST dia as 10 mm. Okay, so we can go for 10 mm column. So we choose 314 3.14 centimeter square, which is nothing but 314 mm square. Okay, so you can choose any value which is greater than required AST. Okay, so I choose 3.14 centimeter square, that is 314 mm square. The corresponding spacing value equal to 25 centimeter, which is nothing but 250 mm. Okay, 250 mm. Okay, so and uh, in other way we have to find the spacing of reinforcement, that is the formula is like AST by AST, small AST by capital AST into 1000. Small AST equal to uh, the cross sectional area of reinforcement, that is 10 mm dia. Therefore pi into 10 squared by 4 into 1000 divided by capital AST, provided AST. Here provided AST equal to so hereafter we consider AST as provided. Okay, therefore AST equal to 314. Apply these values, we will get spacing equal to 250 mm. Okay, then AST minimum. So whenever we find the AST, then compare with minimum AST. For slab, according to IS 456, the minimum AST equal to 0.12 percentage. Therefore, AST minimum value 0.12 percentage of gross area. So B into capital D. B equal to 1 meter 10 power 3 into capital D equal to 140. Okay, say 160 mm square. So our provided AST, which is greater than AST minimum and AST required. So safe. Our providing uh, dimension and area is correct. Okay, the next one is distributor rod. Distributor rod is nothing but the transverse reinforcement. which is over the main reinforcement. Normally 8 mm dia used for distributor. Okay, so distributor rod which is used to reduce the shrinkage. Okay, please note this, as per codal provision, the maximum spacing for main reinforcement as well as main reinforcement and distributed is 300 mm. So spacing should not be greater than 300 mm. Please keep it in mind. Okay. Then distributed, now according to codal provision, distributed should be provided as AST minimum. Okay, already AST minimum calculated, that is 168 mm square. So we provide according to AST minimum. So I said already, I already said earlier, we use 8 mm dia as distributor rod. So go for 8 mm dia column, so 168 mm square. Okay, so we provide little bit greater than 168 mm square. Okay, so we have chosen 201 mm square, that is 2.01 centimeter square, which is equal to 201 mm square. Okay, the corresponding spacing equal to 250. Okay, I have chosen. Okay, you can choose anything which is little bit greater than the required value. That is the main concept. Okay, so here provide 8 mm dia is equal to 201 mm square, 250 mm center to center. Okay, then last one, deflection, because it is a flexural member, it will bend, therefore we will check deflection. Okay, and also the dimension, all the dimension we assumed as per codal provision, that's why we must check deflection. So the condition is L by D max should be greater than L by D provided. Okay, L by D max, this is already which is already seen earlier, L by D basic KC KF. So now AST uh, is known. Okay, therefore we have to find KT value from this graph. Okay, so AST provided equal to AST required value, AST provided for main reinforcement, all those values are known. Therefore mm, therefore FS value we are calculating. Okay, according to this formula 0.58 fy AST required by AST provided. Okay, apply those main reinforcement AST required and main reinforcement AST provided, then we will get FS value, which is nearer to what is the value of FS given in the graph. Then calculate the percentage of value, the percentage of reinforcement. For finding PT value, the formula is 100 AST by BD. So PT value 0.26 something. So FS value and 0.26 value coincide the both values, and take the corresponding KT value, which is 1.5, and apply the KT value in equation number 1. Therefore we will get L by D max equal to 30. Okay, max, this is the extreme, so L by D provided should not be greater than the L by D max. Okay, so L by D provided means LX value, effective span, which is already uh, calculated 3120 mm divided by effect depth 120, that is 26. Therefore L by D max greater than L by D provided, 30 greater than 26, hence same. So our detailing, main reinforcement diameter spacing and distributor diameter spacing and depth of the slab, all the values are correct. Okay, this is the check for deflection. The next step is detailing. The detailing is missing here. That is the plan and section have to draw the next step. Okay, this is the cross section. Okay, the support condition, depth of the slab, the main reinforcement diameter and spacing, distributor diameter and spacing, clear span, support thickness, effective span, all the detailing are mentioned in graphical view. Okay, this is the cross section. The corresponding plan view you have to draw in below the cross section. Okay, this is the last step. Okay, so this is the design of one way slab. If you have any doubt, you can ask me through phone or WhatsApp or mail to me. Thank you very much.